Hello everyone, you are watching the introduction to light propagation in fiber, and this presentation is made by the group of W1C, which consists of Choo Wong Swee and Lim Kok Sang. And what is optical fiber? So the definition goes by the thin flexible fiber with glass core through which light signal can be sent with little loss of strength. And the application of fiber, we could see that this is used in modern days internet, where we use it for transfer of information, and it is very important in these days. So how do a fiber looks like? So this is generally how the core will looks like, and to give everyone an insight of it, it actually looks like a geometrical um, structure. So I'm having an example here, which is a glue stick, and it symbolizes also almost the same with this structure over here. We can see that the middle one of this area is core, and the outer area which provides the reflection, and the reflection is cladding. And all of this is protected by this outer small layer, which is called jacket. So with these three combined, we can see in real life application. So this is core, cladding, and jacket. So the fiber would differs according to its mode, where we have multi-mode and single mode, where the size of the core would change based on the characteristics. So we can actually see that for the structure of optical fiber, there is actually refractive index is different based on the core and the cladding. So for a core to completely reflect within the fiber, its refractive index must be greater than the cladding, must be greater, so to provide a total internal reflection. So what is all this total internal reflection all about? So I will explain it in the next one. So actually we can see that uh, in the fiber, it's all about light propagation. So light propagation, we can actually see is that a simple explanation via ray optics, where this is actually from the inside of the fiber. This is the core. This N1, the blue area, is the core. N2 is the cladding. So the red ray and the blue ray represents the light ray. So when red, it goes through in a straight line, it would appear a straight line, yes. But if it goes through the angle other than straight, which is not 90 degrees to the surface, it will reflect within the core. So how do they do that? So it's actually based on two significant laws, which is very helpful in the reflection and refraction as well. So the first one, it would be law of reflection, and the second one is Snell's law. With these two, it is theoretically proven that with the law of reflection, the angle of incidence would be angle of reflection. The second, for the Snell's law, N1 represents the refractive index of the core, and sine theta 1, which it could represents the angle that the light rays enter the core, is in the is the incident angle. So it will equals to the N2 refractive index of the cladding and the transmitted theta. So let's demo this general rays that enter. So the first one, let us draw a simple light ray, which we include as incident theta. Let's draw a normal incident. So with the law of reflection, it will go The incidence angle would be equals the reflection angle. Reflection angle. So for the Snell's law, so the N1, sorry, we would use this area as the core, and this as the cladding. So for N1 and N2, when the light ray enters, it will go N1 with sine theta 1 I equals to N2 sine theta t. So let's explain about total internal reflection, where it moves to here, and how the total internal reflection occurs. It is when the transmitted angle over here is equals to 90 degrees, which is like this. The incident angle would become the critical angle. So as theta I increase, the theta t increases, and the theta t until 90 degrees. So it appears that theta I would be like this. Theta I. So N1, N2 again. And so this theta I will become theta critical angle. So how do this critical angle would helps in transmission of light? So we can see that if theta 1 is lesser than critical angle, the ray refracted and reflected, so there will be some energy loss when there is reflection. But if the theta 1, this, which is the incident angle, which is greater than theta critical angle, the ray will totally reflected, where there will be no energy losses throughout the transmission. So back to the graphs, where we are going to discuss about the acceptance angle of the fiber. So when the light ray enters the cord and the fiber, they would have an acceptance angle where the light rays would enter according to an angle, and it will be reflected completely inside the fiber. So what is accepted angle? The angle that optical fiber below, which rays are the guided rays. So to have a visualize of the acceptance angle, you can see that it's actually represented by a cone which is in front of the core. So all the light rays which enter through this area, it will be reflected inside this core for the transmission as well. So with this, we can actually tell that actually there is a numerical aperture. This is a further graphic that could explain the acceptance angles. So we can see that actually this is a cone. So the light enters inside the cone, it will be reflected. But if the light enters to the outside of the cone, it will like this. It will go refracted inside the core. So the total internal reflection could not work throughout this reflection thing. So talking about the acceptance angle, we will refer to something called numerical aperture, which is the light capturing capacity. I'm sorry. So there is some equation involved for this numerical aperture. Numerical aperture, we would refer as NA. So NA would equal to theta sine max. This is the acceptance angle. So N1 cos theta critical angle equals to N1 square minus N2 square and the square root of it. So we can see that numerical aperture. So this would be the light rays enter inside the acceptance angle. So it would reflect with a total internal reflection, and it would be perfect inside the fiber transmission. So this would be the end of our presentation. Thank you very much for watching. I hope you enjoy it. Thanks.